All right, let's go get started. So I think the couple quick announcements that were that I put on Canvas as well as Slack is that kind of adjusted and finalized the schedule of due dates for the concept checks and the mini projects. I tried to organize things so that you got roughly a week and a half to do a concept check after we've covered the material, and then whenever possible, then at least a week later to do the mini project associated with that. So you had a chance to kind of marinate in the material in lecture, get kind of a chance to play with it in the concept check. And then after that, then can try it out for the mini project. And then with respect to the mini projects, and then I also sort of, there was before with that natural kind of spacing of things would have put both like a concept check due at the beginning of spring break and then at the end of it. And so I just moved those so that there's the weekend after spring break, you'll see there's two concept checks due at the same time. And that wasn't meant to load things up there. It was meant to sort of provide more flexibility. So all these things are already available, so you can do them at any time. So if you'd like to turn them in close to the due date, that's fine. If you'd like to turn them in ahead of time, that's fine too. With regard to the mini projects, again, I think it automatically drops 5 mini projects except for the first one. So there are 7 mini projects after the first one. And that first one you can turn in until tomorrow, Wednesday night. And so after that, again, there's 7. We automatically drop 5. That means you really only have to do 2 mini projects from here on out, and that you're 2 that you're happy with your performance on. So you can kind of pick and choose from the 7 that are available. I've highlighted 4. I think they're mini projects 3, 4, 5, and 6. I think it says on Canvas for sure to get the numbering right. And a reason I highlighted those is that the other mini projects are either going to be a little more abstract, like the one on genetic programming. Unless you're already sort of into that, it might be difficult to kind of get a quick mini project up and running, or they're going to happen kind of late, like the very last mini project, right after we sort of talk about it in the class, then we don't really have a whole lot of time to marinate in that to do the mini project. But what's nice about 3, 4, 5, and 6 is that they all can be done in a similar application as mini project 1. You can come up with a simple kind of numerical optimization problem. Even you could even use, at least for one of your optimization objectives, the objective from mini project 1, and then work from there. And so those can be relatively short, and they don't require a lot of additional background or a lot of additional support. So that's the reason I'm recommending those. And so there's 4 of them recommending, and again, you don't have to pick like 2 of those. You can do all 4 if you'd like, if you want the practice, but the only requirement is you sort of have to do 2 that you're going to be happy with your grade on. So so that's the way things are kind of lined up. So that's I think all of the important things. I haven't got through all of your muddiest point submissions to see if there's any comments to be made. I've gotten through a couple of them, but I'll try to knock the rest of them out today. If not today, then tomorrow. So any questions about the lineup of things? Yeah.
When you said that you want us you can work ahead on the concept check, how would we do that if we need to actually learn the concept from class?
Well, the idea there is there's going to be a gap, and so just because it might be like we might finish the concepts on a Thursday and it might be due a week and a half later from that, that sort of thing. Additionally, there are readings associated with every unit, and you can also watch the lectures from last year. So for whatever reason you want to get all the content from the course, but you don't want to move at the pace that I'm moving at, you're free to watch the lectures from the last time I taught it, or read ahead. Those sorts of things I'm happy with you to do as well. So I'm just trying to give you options, and the due dates are just sort of meant to put kind of waypoints, but you can kind of improvise if you want to turn things in early. All right, any other questions? I don't see any questions online. Let me see, maybe I do. No, okay. Great. All right, so now we're talking about multi-objective optimization, which is one of my favorite topics. So we started talking about it a little bit last time, and I said most of the time when people think about multi-objective or multi-criteria decision-making, then the first thing that comes to mind is game theory, and where you have a number of players. So we'll say n players that each have a utility function UI that provides them a reward. So I'll say I is in 1 up through n. But although it provides them a reward, their reward is determined not only by their own actions, but by the actions of everyone in the game. So that's generically what sort of game theory models these types of problems. And one solution concept, so there's the solution concept that we talked about last time called the Nash Equilibrium. And we talked about it more in detail last time, but the basic idea is in this solution concept, it is the set of plays across all of the players for which no unilateral changes can cause any one player to do better than they're already doing. And so there can be multiple Nash equilibria in a game. There can be no Nash equilibria in a game. Very often, in the economics literature and so on, the focus is on the equilibria themselves. What do they look like? In the numerical optimization literature over in computer science, it's often focused on, do you have an algorithm that can find a Nash equilibrium while it's sort of operating? So if you have like a bunch of robots running around and they're all following their own gradient, they're all doing what's selfishly useful to them, like, they're all trying to climb uphill. Will this team of robots manage to come into some agreement on what their strategies are? Now, those strategies might not be the best for the group, but they will be somehow stable in terms of individual level utility, individual level rewards. And so this concept, at least in engineering, is particularly useful when you have no communication or coordination between agents. And so it's a basic idea of, I know that the reward to each agent in my distributed system depends upon the actions of the others, but I have no way to coordinate their actions. So all I can do is have each agent respond to its local rewards through like a reinforcement learning type approach, and then ask, what does the group converge on, given that they aren't coordinating with each other? And that is the Nash equilibrium. And that is one solution concept we have when we have multiple utility functions, multiple stakeholders, multiple criteria that we're interested in. We're interested in, so let's say, for example, the energy use or the amount of dirt found by this Roomba and the amount of dirt found by that Roomba. Those are, if this Roomba sucks up more dirt than that Roomba, it's going to prevent that Roomba from maybe getting as much reward because it gets a reward for how much dirt that it sucks up and vice versa. So they can be coupled together, and choices made by one are definitely going to affect choices on the other. So there's these two stakeholders there, but everybody's kind of going it alone. So that's one solution concept. Now, another solution concept that we're going to get into here is the so-called Pareto equilibria. And this is, another solution concept. So, and so I'm just going to introduce that here with a knapsack example. So I'm going to flip my page here and start this knapsack example, and that will motivate this other solution concept. And this other solution concept has a lot more connections to biology. It's, I think, a much richer and more interesting solution concept. And if you're building decision systems that are autonomous systems that augment the intelligence, we are the School for Computing and Augmented Intelligence, right? So we're augmenting the intelligence of human decision makers. The Pareto solution concept we're going to see, I think, is a much more useful solution concept that brings all these things together. So let's see how that looks. So imagine as an example, the so-called knapsack problem, which many of you have probably seen before, and you've probably solved it in a not very Pareto way. So, so the idea here is you've got n items that you want to put, let's say, into your bag, into your knapsack. And so each item, not item, each item, I, has a weight, WI, and profit, PI, associated with it. And so, of course, the heavier the objects, kind of the worse they are somehow, but the more profitable the items, the objects, then kind of the better they are. So there are these two conflicting things that are going on here. So we want to say which items to put in our knapsack. That's the fundamental problem. Now, so if we were to think about it here, we could plot out the suspense, right? I draw two axes and you're like, well, what's he gonna put there? Like, what's gonna be on this axis or that axis? So I'm both of these, I can say I've got a number of items, but I can plot out, let's say, the total profit on this axis, which you might say is just the sum of all the PIs for all of the items in my knapsack. So I'll say all my items in the knapsack S. And then on the other side, I can have total weight, which is just the sum of the weights for all of the items in my my set. And so if you think about this, both of these functions look similar, just with a different slope, right? So as you increase the number of items, then generally, whatever this function is going to be, it's going to be something that's going to climb in this direction. And likewise here. So in both cases, as you increase the number of items, you're going to increase the value of these functions. But this is the good direction for profit, and this is the good direction for weight. So that's the fundamental problem in the knapsack problem, is that, yeah, I could increase the number of items in the sack, and that's going to benefit me in terms of profit. But with every item I add in sort of the sack, I have to pay a cost, because now I have to carry that thing back. And it's interesting, you actually see plenty of knapsack problems in nature. Honeybees, for example, they have to, when they go and they get nectar, they fill up their crops with nectar, and it turns out that it's very costly for them to fly back with a full crop because it's heavy. And so, they have to deal with these sort of things too, of exactly how much do I fill up? So this is like a fundamental problem, the knapsack problem here, and it generalizes to a bunch of these things. So the question is, how do you decide which items to put in your knapsack, or even how many items to put in your knapsack if like they were all roughly the same weight or something like that? And there's a bunch of different ways that you could do this, but they all come down to sort of saying, what's more important, my total profit or my total weight? So what are some of the methods that you might have heard of, or that you might think of for solving this problem? Yeah.
You do like a profit to weight ratio of items, and then the ones that are like a ratio that you might put down. Those items are good to carry, while ones that like have a low ratio, then you might be.
So you're suggesting there's a heuristic where you could create a profit to weight ratio, and those that are above a profit to weight ratio threshold might be taken, and those below might not be taken, which is a strategy you could use. But then you might have to ask, well, then what what would, like, what does that heuristic do? So I guess you would say is like, how do we know that that heuristic is, like, how does that heuristic, do we know that that heuristic is mainly profit-based, or do you think it's more weight-based? I mean, so where, in other words, is there a way for us to say, a way that that heuristic could pop out as a solution, like a more mathematical way? Because there's another approach that's sort of a little more high level, where that might end up being the solution to the approach. Let me see, I see a comment online. I've got the weight of the items aren't the same, right? That's true. The weight could be different across the items. And someone says linear programming with constraints. Could this be used, I guess? And that's fine, the linear program, but then you have to say, what is the linear program that you would use? And that's kind of what I'm getting at here. What is the correct linear program for merging these two concerns? Yeah. Pardon me?
Simplex method.
Well, so simplex method is how we would solve a linear program once we formulated it. How do we even formulate the linear program for this? Because a linear program would be, something like minimize f or maximize f subject to a certain number of constraints. Well, what is the f? Am I doing it with this one? If I'm doing this one, what are the constraints? So, how do I even formulate this problem? And how do I do it in a way that is going to satisfy everyone who I could possibly talk to about the Napsack problem? So, I mean, so like as an example, so let's bring it up. So the linear programming has been brought up. So something you can do, a typical linear programming approach would be like one option, would to do what we refer to as satisficing one objective. So the idea here is that we're going to take one optimization objective and say we do not care about optimizing it. We just have a minimum or maximum threshold that we have to abide by. And as long as we are under or over that threshold, then we're okay. And so a satisficing solution might be maximize profit. So I'll call profit FP, and I'll call weight FW. And I can say maximize profit such that the weight FW is less than or equal to some maximum weight. So this is a common way that you can solve a knapsack problem, is you can choose a budget. This is a weight budget. And then so long as you're under your weight budget, then you just maximize your profit subject to that budget. But then the question here is, how do you choose the budget? Some people have bigger budgets and some people have other budgets. Others are really going to be more concerned with weight. And so you could say, well, what if I instead say minimize weight subject to a profit requirement? And that's another way you could possibly do this. But there's going to be some people who are happier with this objective than with this objective. So just by choosing the optimization program, both of these can be solved with linear or nonlinear programming methods. So so in this case, because f of p, this is all nice and linear, you could just take the simplex method or something and solve either one of these. But which one of them is the right solution to this method that balances these things? Can somebody else think of another way we could use optimization approaches to blend these two optimization objectives? You got two objectives, one that you like to minimize, one you like to maximize. There's another question about there's another comment about using dynamic programming. We have to sort of say, well, again, how do we write out the dynamic program for this? Is there another objective that might easily blend these two objectives together? Maybe, for example, we could say, do what I refer to, and it's not my term, but it's not necessarily, it's more of a conventional term than a standard term, is scalarization of objectives. In which case I could form a new objective, let's call it G, that is equal to, or I'll just cut out the middleman. I'll just say, well, what if I want to maximize profit minus some weight times weight. So there's here just a scalar. And so in this case, I create a composite optimization objective where I can choose how important profit is versus weight, encode that into this here, and then turn this into a new optimization objective. And this is now a simple single optimization objective. And it blends from both of those together. So now, rather than satisficing, where I just, as long as I'm under a threshold or over a threshold, I'm fine, I at least am respecting the fact that really heavy knapsacks are going to be penalized, even if they have high profit, and really light knapsacks that have high profit are going to be elevated. So this is another way to do it. But again, the problem is, how do you pick the scalar? So who picks this? Pardon me? Oh, the B, right, exactly, the B picks it. The stakeholder picks it. Ideally, you would like to walk up to whoever, you know, the marketing person or whoever you're trying to solve this complicated computational problem for and say, hey, what do you want that to be? And they're going to say, I have no idea what that means, right? I mean, so this is something that makes sense to you as a nice way to balance these two objectives, but it doesn't make sense to them. They'll say, well, what happens when I set it to 0? What happens when I set it to 10? Is 10 big enough? Do I need it to be 100? What, you know, like, so now it becomes a whole nother problem of choosing the right value of that. And what's going to end up happening is you're going to choose some value. It's going to come up with a solution. Your stakeholder is going to look at you and say, I don't like that solution. Can you try a different balance? And then they'll put a different one in there. And you'll end up basically giving them a set of possible balancing solutions between these two things that they end up choosing between. And that's really what we're trying to get at, that type of solution concept, this kind of set-based outcome. Now, the other thing we can do, is I'll just throw that in here, is like option 3 is that we can do, you can set targets and try to get as close to them as possible. So this is almost like a regression problem where you can say, let's say, for example, minimize the distance from these targets. So I can say minimize my profit, let's say squared plus my weight. That would be one way to do it. Or I could maybe say maximize my distance away from given targets. So these are another option here where if somebody said, I really would like to make $100 by carrying 20 pounds on my back, you could put the 100 and the 20 in there, and then you could find whatever knapsack combination is going to get close to that target. Or you could say, oh, you want to make at least whatever I said, $100 with at most 20 pounds, and then maybe this will have a way to sort of nicely balance those two. But then who chooses the targets? And so again, your stakeholder has to know these targets ahead of time. So we would like to come up with an optimization method that blends these two optimization objectives and just gives us an idea of how they trade off with each other, so that we don't have to ask our stakeholder for arbitrary numerical thresholds or scalars or whatever, that we can just show the stakeholder that this is the best you could possibly do for this weight and this profit, and show that for all of the weights and all of the profits. Yeah. Not on the second one. So the first one I did, but the second one, you can kind of think of this as like, you want these, ideally these will be positive.
Oh, so it doesn't matter.
Well, if the optimization works, it will find solutions that are positive. And so then it won't matter. In fact, I don't want to put the squares there because the squares well, I mean, if I put in the squares, it just turns it into this one up here. So this one tries to regulate around the thresholds. This one is okay with being over threshold, but penalizes being under. You know, so yeah, but there are all these tricks we can do of writing the problems. But what I'm trying to get to here is all of these frameworks where we're trying to shove two optimization objectives effectively into a one optimization objective framework are going to leave something out and are going to require us to ask uncomfortable questions of the stakeholder. So it's not ideal. So really we want to say, well, what's another thing we could do? Let's think more about these problems. And so a more intelligent way to think about it is you could say, well, you know, let's just, for kicks, I'm going to plot, and this is where we get to Pareto. I'm going to plot both optimization objectives on kind of the same axis, one objective up top, one down below. And I'm going to be a little bit more generic here. So I'm going to call this one up top F1, and this one below I can call F2. And I will say that it is good to be in this direction on F1, and it's good to be in this direction on F2. And I've got some variable X, and let's say that if I plot X, or if I plot F1 over all values of X, I get something that maybe looks like this. And if I plot X over all values of F2, then I get something that maybe looks like this. Okay, let me make sure that I got my points in the right pot. So I've got a max of F2 here, a max of F1 here, and I could just project these down just so I have guide points here. Maybe I'll go all the way. All right. So now, rather than asking the question of what is the best X, it's kind of like, you know, this is a matrix reference. There is no spoon. There is no best X. But there are bad X's. There are X's that you should never, ever choose, regardless of how you trade off one F1 versus the other. Does anyone see an example of what I mean by X's that will never be picked by this? Why 0? That's right. So it's bad in both, is what you're saying. So that's a great example. So X equals 0, I can put over here like X equals 0 is uniformly bad. So it's right here, X equals 0, uniformly bad. And so, let me make sure I don't miss any comments online here too. So there were some comments online about the previous penalty functions. And again, that's true. We can form all sorts of penalty-based functions, but we all are stuck with these penalty terms that we have to figure out some way to deal with. And so someone had said outside the little dotted rectangle seems bad. So I think that's a nice generalization. So if I look at this rectangle, think about it. I'm going to try to keep my pointer on here. I think it'll stay there. Anything to the left and right of this rectangle is bad. You should never choose an X that's in this region or in this region, because in those regions, there is always a way you could do better in both objectives simultaneously. If you think about it, if I was sitting here at this optimization or this decision variable value, and I were to go up to this one, if I go to the right, I move in the right direction, the correct direction. If I go down to this one, if I move to the right, I also move in the correct direction. So if someone were to propose that this was the optimal solution, you could propose a solution a little bit to the right of it and be better in both. So that tells me that these regions, choose a different color maybe. That tells me that these regions right here are just bad regions. You should never pick anything in that region. Yeah.
And what prevents us from like just saying, let's try to maximize this, you know, F1 squared plus F2 squared, and then we'll get the exact point in that rectangle that maximizes the overall between both.
Well, so the question was, why don't I just maximize the square of both? If you do that, though, you are taking a stance about how important one is versus the other. Like you could say, why don't I maximize f1 squared plus half f2 squared? Yeah, well, that's the point. The scalar there, you don't know what that scalar is ahead of time. And so what I'd like to tell my stakeholders is, rather than this is the solution you should do, and they hate that. When a computational person comes to a policymaker and they say, you need to set exactly this tax rate or whatever, they hate that because they say, well, what do you mean? Like, you know, all of my experience, whatever, they need a degree of freedom to work. And I don't blame them. What we can do is we can say, you should definitely not choose any of these values of the decision variable, then you're free to choose anything in here. So if you have another criteria you can use about the balance between your two objectives, then do it in here. And then this here, this region, we can say will correspond to these values of F1 and these values of F2. And those there, we can characterize that trade-off. I mean, now you can see that if I'm at this point here, if I go to the right, I'm going to increase in one, but I'm going to decrease in the other. So now I can actually start to characterize the trade-off between the two variables and let the stakeholder decide. So what I've done is computationally removed the definitely bad solutions that you couldn't choose, and then given them as a solution. So if I were to highlight, then I can say these here are the so-called Pareto Efficient Set. And we refer to them as being Pareto efficient because there is no way to make a so-called Pareto movement away from any point in that set. Now, what do I mean by Pareto movement? A Pareto movement improves all objectives simultaneously. So we say that the points in here and outside here, outside this region, from those, I can make a Pareto movement. I can make a change in this decision variable, say moving to the right or moving to the left, that causes all of the optimization objectives to go up. And that means that they are Pareto inefficient. This set here is the set of so-called Pareto efficient sets. And that means a Pareto efficient, they're all of the points from which there is no Pareto movements, there are no Pareto movements. And that is something that if you give me lots and lots of optimization objectives, it is a useful computational task to solve for the Pareto efficient set. Question? If you take a value of x and you put that value into both these functions, and if you find that if the product of the gradient is negative, then that value is higher. I'm sorry, if we find that that which? Oh, well, if right, okay. Sure. So right. So the way so there's a question about, can we check these with sort of the gradients of these things? And of course, if you have the functional, if you have the analytical form of these things and they're differentiable, then you can use gradient information to determine if there is a Pareto efficient, if there is a movement out of there. Traditionally, you can just solve by these for finding existential witnesses. And so if you were to stand inside the Pareto inefficient set and then do a test where you're to step in all possible directions, if you didn't have that information, if you were happen to find a direction that improved in all of the optimization objectives, you would kill the one that you were just at, and then you would consider the new point as a potential Pareto efficient. And so we keep doing that until we can exclude everybody except for these. So these are the ones that can't be so-called dominated by another one. So we'll talk about this term dominated here in a second. All right, so does this make sense so far? What I mean by Pareto movements and Pareto efficient. This is a totally different solution concept. When you give multiple stakeholders, it's what are the things that aren't the things that, if there's something that can make society better, we should do that. But we want to live in the Pareto efficient set. If all of us have a utility function, we would like our society to be somewhere inside here. What that means, if your society sits over here, that means that there is a way for someone in the society, the government or whatever, to make things better for everybody. We do not want to live in a society where things could be better for everyone if we all just changed. We want to live in a society where the only way things are better for someone is if they're worse for someone else. That sounds a little bit bad, right? But think about it as in like, if we're in this set, that's where real interesting decision-making happens. This is dumb decision-making. This is just, can I make things better for everybody? If you can make things better for everybody, make things better for everybody. Nobody loses by making things better for everybody. We want to live in the region where the only way someone could be better off is if someone else is worse off. That's what the Pareto efficient set is. Yeah. Yes, absolutely. So there's the question of does the Pareto efficient set exist, and how big is it, and so on and so forth. And you can there will always be a point in the Pareto efficient set. So in the worst case scenario, you'll get a singleton Pareto efficient set. So where it's just that, you just happen to be that there's so many optimization objectives that there's no way to make them all better for everybody. So it always exists, but we want to see that what is the degree of freedom of this Pareto efficient set? So do we have any room to move? Okay. All right, so that's the, let me make sure there's no questions online. So there was a question here, I think, looking ahead. So something inside the Pareto rectangle is so-called Pareto optimal. I'm about to introduce Pareto optimal here in just a second. So, but for now, the term that we have here is Pareto efficient. All right, so now there's another way I can visualize this. I visualize this in the decision variable space, and I just did a single decision variable. If you get multiple decision variables, a large decision vector, multiple dimensions, high dimensional decision vector, then this becomes hard to visualize this way. It's very common that you're going to have an extremely large decision vector, but only a couple of optimization criteria. And so it becomes more useful to picture this in kind of an optimization space where I consider a plane or whatever a manifold is the dimension of the number of optimization objectives. Where in this case, let's say I put F1 on this axis, F2 on this axis, and so these could take as arguments an arbitrarily large decision vector. And so now I just do a parametric plot of all possible outcomes I can get for every decision vector. What is F1 versus F2? And what I'll find is that if I, for some decision vector, I get this point here, for another decision vector, this point here, another one here, and so on. If I were to just sort of randomly search through all of my decision space, and then for every point that I found, I plotted the F1 and the F2 together, then I would start to fill out a space here. But that space would eventually have a region where it would not move beyond. And so you would end up getting this line at the edge of this region. And there might also be, I guess I'll just go all the way back to here. There might also be voids, down here and here. So it might be that you only exist in this region, but if I'm trying to maximize both F1 and F2, ideally, there will eventually be a point or a line where there are going to be no points that are out here. And this line here, we refer to as the Pareto Frontier. The frontier, the boundary. So it's the boundary of all optimization criteria that are possible. That's what we've got here. And so this characterizes the trade-off between F1 and F2. So in other words, the points that I plugged in to get this line here, those are the Pareto Efficient Set. So if you plug the Pareto Efficient Set into the optimization objectives and then plot the optimization objectives, you get the Pareto Optimal Frontier, or the Pareto Frontier. And but all of these points here, these are Pareto inefficient. So I guess I could draw that if it's helpful. So these points here are not Pareto efficient. And that should make sense because we could start on any one of these points and make a movement that would be better in both optimization objectives. Once we hit here, the only way I can move along this frontier is if I go down in one optimization objective and up in the other, or vice versa. So that's what characterizes these things. So this is usually a much more useful way to plot out these frontiers. Yeah.
So in the example where X was just a single variable X, was that section, the set of X values in that rectangle we drew earlier?
Yep.
Is that the same set of X values on the frontier?
That would be, this would be the image of those. Yeah. And so, yes. So if you projected these values here through F1 and F2, and then plotted what you got out, you would get this thing here.
And then everything under are the orange X's.
That's right. These here correspond to all of these under here. Okay. All right, does that make sense? It's the image of the Pareto set, or the Pareto efficient set. I would say that sometimes we call, sometimes we do call this the Pareto set, just to be concise, just like sometimes I call this Pareto Frontier, but it's also known as the Pareto Optimal Frontier. And then sometimes people would call this the Pareto Optimal Set. So I hope you see the pattern that set refers to the decision variables, and then frontier refers to the optimization objectives. All right, let me see if there's any questions or clarifications online. All right, looks like it's the same. Any questions in class? Does this make sense, these concepts here? Now, so the reason we talk about this sort of thing is that, again, this is I find that this ends up being a very useful construct in realistic optimization problems with multiple players, or just multiple things you care about. You care about the energy use, you care about how fast, you care about how long the robot lasts on its battery, but also how fast it gets the jobs done, and so on and so forth. And very often you don't know, how to balance those. But if you can show me this frontier, I now can do also, like if this frontier is vertical, then that tells me really important information about this trade-off. That means that regardless of what values I have in one optimization objective, the other optimization objective doesn't move. So there's really no trade-off. So in that case, it is possible for me to have the best in one optimization objective without paying any cost in the other optimization objective. Likewise, if it was this way. And then if it's, if it's slightly slanted, then it kind of gives me that it's a cheap trade-off. And that, in other words, for very little cost in one optimization objective, I get a huge benefit in the other. So if you can show me these frontiers, then rather than coming up a priori and just saying arbitrarily, I want a 50-50 balance between these optimization objectives, show me the whole frontier. And then I'll say, wow, I thought I wanted a 50-50 balance, which would put me here. But now that I see this, I'm willing to give up a little bit of performance in one objective to get a huge amount of performance out in the other objective. So it's an extremely valuable way to characterize the optimization space for multi-objective problems. Yeah.
What if you don't only have two objective functions, let's say you have four, or you
sure.
What's the technique for actually knowing what the frontier is?
Excellent. So there's a question of if you have multiple optimization objectives over 2, 3, 4, 5, it does become more difficult to visualize this space, this frontier, but it's not impossible. And you can take cross sections of it and so on and so forth. And so now we get into kind of a computer visualization or a UI sort of thing, like how do you interact with this manifold? But you can interact with this manifold. People can then ask you, I have these 5 things I care about. Can you tell me how does thing 1 trade off with thing 4? Okay, how does thing 1 trade off with thing 3? Oh, I see that with a little bit of cost in 1, I may not get much benefit in 4, but I do get a lot of benefit in 3, and they can start doing those combinations. Right, for example, that'd be one way that you could handle it. Yeah. Question in the back?
This is the same problem where you can decide how much weight you're assigning to each one because, I don't know, the graph that you drew could appear to be more of an even trade-off where you think dollars versus cents.
Right, so that's a great point. So the question, doesn't this still have subjectivity in it? And it does, but it's honest about the subjectivity is what I'm trying to say here. So we can decide ahead of time that we want a particular, this many dollars for this many pounds. That's effectively, when you go back and choose a scalar like this one, I mean, if you think about the units for this scalar here, you are choosing a dollar to pound, ratio out of that. And if you optimize this thing, you'll actually you'll solve for a point on the frontier. It won't be off, it'll definitely be on the frontier, but it'll just be some point on the frontier. All I'm saying is, if you had a hard time coming up with that scalar ahead of time, effectively solve the problem simultaneously for all of the scalars. And that gives all of these things. And then say, can we find something more intelligent? If you look at this and it's still gobbledygook, fine, well then just pick a random point, because that's basically what you're doing to begin with.
This one is better if you don't have the domain expert beforehand, but you want to generate this and present it to the domain expert.
I think that's so. Yeah. So the question was, is this good for when you don't have the domain expert and you want to present it to the domain expert? That I think is an excellent use case. The other case I found in practice is domain experts don't quantify the things that they need very well, often because they don't quantify the trade-offs, often because they're in different units. So they'll say, like, I work on a flood risk simulation that has to do with, like, what's the risk of a certain type of flood in a month versus a year? And then also, how much storage do we have in a reservoir? There's all these like things, or there's probability versus gallons or whatever. And so ahead of time, I could either like tell them like, well, here's the best operational profile based on what I think based on what I think is important versus flood versus storage. But in the end, I find it's just easier for me to come to them and say, rather than trying to ask them, is it 5 times more important for you to have, flood mitigation versus storage for drought? Because then they're like, well, why 5? And you might be able to survey them and maybe they'll tell you 5, but maybe on a different day, they'll tell you 10 or 100. It's just easier for me to say, well, okay, here's actually the trade-off between these things. Sometimes there will be no trade-off and we thought there would be. Sometimes there's a huge trade-off and really got to get it right. And then we know where we kind of need to do the research better. So for me, this captures a really important edge of the optimization space that I think is much more important to know ahead of time before you start scalarizing things. Any other questions about this before we start talking about algorithms that actually find these things? Mm-hmm.
Just slice that part up, and then that would be part of your frontier, or that not part of your
Yeah, so there's great. How do you deal with constraints? If you did want to do the satisficing, where you need to say, I need F1 to be at least this big. Well, that's great. In this space, you can just sort of say, well, I'm only going to consider this part of the frontier, you know. Okay, let me see if there's anything online. Okay. So I think I already covered that. The frontier is exactly the same as the efficient set. So the question line is the frontier exactly the same as the efficient set? When we use the term frontier, we're referring to the optimization space where we're plotting objective versus subjective. And so that's the frontier. So frontier implies optimization functions. When we use the term set, we were actually referring to the decision vectors that are the pre-image of the frontier. So the image of the set is the frontier, the pre-image of the frontier is the set. So that makes sense. Okay, now, fortunately, evolutionary algorithms are great for solving multi-objective problems. Does anybody have a guess as to why evolutionary ideas or evolutionary computation is ideal for solving multi-objective problems? What's fundamental in every single evolutionary algorithm, be it a genetic algorithm or some other variant, what's fundamental to evolutionary algorithms? How do we solve what's going on every generation?
Survival of the fittest.
I hear survival of the fittest online. I hear selection. That's true, but in order to have survival of the fittest or selection, what are you sort of presupposing you've got running around in the background? Pardon me? There's multiple objectives, but I'm looking for another multiple. You got multiple candidates, you got a population. So that's what makes them great about this, is that other algorithms that consider a single candidate at a time, remember those, I saw those trajectory-based methods like taboo search and things like that, those really only can evaluate one objective at a time. Well, they can evaluate multiple, but they can't sort of simultaneously search this complex space. But what's beautiful about evolutionary algorithms is we can unleash them, and you can have multiple individuals that are not converging to a single point. We know you should, I mean, those of you who finished your mini project 1 know that if you had really high selective pressure, you might have got all your points to converge to the top of one of those peaks. But my guess is that a lot of you, and I know I went through a lot of your solutions, several of you always found the peak, but you had these stragglers that were hanging out next to the peak, or maybe way over on another peak. And those stragglers seem useless when you've got a single optimization objective. But when you're solving these multiple objective problems, then you use the entire population, and the population becomes a sample of the frontier. So the output of a multi-objective optimization problem, multi-objective evolutionary algorithm, is going to, if you do it right, you'll get all those points will end up being points as close to the frontier as possible. So our goal in designing an algorithm to solve multi-objective problems is to get rid of all the Pareto efficient or the Pareto movements. So get rid of these points so that the population that comes out is this line, and it is spread as diversely as it possibly can across that line as possible. So that's the great thing. Most other optimization objectives focus on a single point. And so if I wanted to find this Pareto, the way you do it, like with a standard linear programming method, is you would go back and you would solve your LP. You'd solve this, for example, in your optimization algorithm with different values of this scalar. And depending on if you've got well-behaved optimization objectives, if you solve this for a bunch of different values of this scalar, you will etch out that Pareto frontier. But we are not having to resolve it every time. We can solve in one go. We have our entire population search for this frontier. And so what we're going to learn about in this unit is how to move points close to the frontier while keeping them from moving towards each other on the frontier. So there has to be attraction to the frontier, but repulsion along the frontier. And that's what we have to generate in these multi-objective algorithms. Yeah.
When you're talking about the sigma, so each point on the frontier, right?
Yes, yes. I could just put that here in case it's helpful for somebody else. So this might be sigma equal to 1. This might be sigma equal to 2. This might be sigma equal to 3, and so on. And so that's supposed to be sigma equal to 3. And so you could imagine here that as, you know, in this case, as sigma goes to infinity, then the multi-objective goes to a single objective. And so, so as you're moving, sliding down the frontier, what you're actually doing is saying, I care less and less about one objective, more and more about the other, until eventually I'm only really optimizing a single objective. And that's what slides. That's right, exactly. Yep. All right, any other questions about that? I want to make sure we're all, you know, we all got this solution concept in our minds. Pareto optimal versus Nash optimal. There are cases where you can be both Nash optimal and Pareto optimal, but in most of the interesting cases that we talk about, there's a difference between the two. And so if you let things go on their own, then they would be Nash optimal. But if you have some way to coordinate, maybe with the central decision maker or communication, then you're aiming for Pareto optimal. Okay, so how the heck do we do that? So, sorry, so I'm flipping between the last couple pages of last lecture's notes and the first couple pages of this lecture's notes, trying to make sure I get to the right point. Okay, good. All right, so how do we solve? And so let's, we're gonna get inspiration from nature. So let's do, and we started at 10:30, so I'm watching my watch. And so nature is all about trade-offs. And I've kind of hinted at this already. So we would expect natural selection to eliminate Pareto inefficient strategies. So, so the basic idea here, let's review, you know, we've got our decision vector. I'll choose a different color. We've got a decision vector X that we are calling a chromosome. And so particular values of X vector, we're calling you know, that's the strategy or the genotype. I'll get that in a second. So then the decision variable, this is again, just all review, XI, that's what we're calling the gene. The strategy or the candidate is, you know, a particular value I'll call X star, and that is the genotype for that individual. So this is like an individual. Okay, now, before we were only working with one objective. I talked to you about how we're, a hint of how we're gonna incorporate multiple objectives. Now we're gonna drill down into that. So we have objective 1 in our optimization problem, and we'll call it objective 1 F1. And this is what I'm gonna refer to as character 1. So when biologists refer to an organism, there's a number of different characters. There's the eye color, there's the shape of the nose, there's whether the earlobes are connected. All of these are different characters. And if you're looking across different species, you can use different characters to sort of tell, is this one species or another? But even within a species, then you can have different character states, which are known as traits. And so, so each character has its own, I'll say, with trait values. So we can say that this individual, when I say it is evaluated along a certain optimization objective, you can think of that as saying, what's its eye color? So I'm not saying currently what eye color is best. That's what the fitness function will be for. But I can still think of the optimization objective as mapping out like an eye color, and the particular value of the optimization is the particular color, like brown or blue. So then I can have another optimization objective. So objective 2, f of 2, and this would be like character 2 with all of its trait values. And so if you don't like eye color or whatever, I can actually think of optimization. Character 1 might be the average speed of the individual. Character 2 might be the individual's basal metabolic rate. And so I know that a particular individual can run very fast, but if I happen to also put it on a respirometry machine, I can see they also burn a lot of energy even when they're sitting still. And so I could imagine that it's important to run fast, but I could also imagine it's important not to burn a whole lot of energy. I don't know what's the right combination of those two, but I know that both of those are possibly interesting and useful. That's what makes them characters. So characters are things on which selection might act simultaneously while acting on other characters too. So I can have multiple characters. So I can go all the way up to objective n. And so I'll call it f of n. And so again, this will be same deal, character n with trait values. Now the suite of traits is called a phenotype. So I can say this individual runs really fast and has a high resting metabolic rate. It burns a lot of energy even at rest. That's their phenotype together, those two things. I can say this other individual, they run really fast, but actually they do not burn a lot of energy at rest. That's their phenotype. So each individual has a different mixture of how well they do along these different character dimensions. And we could imagine that maybe selection would favor lower metabolic rates and higher speeds. And so between those two individuals, we would favor the really fast one that doesn't use that much energy. But if there was another individual that used very little energy, but is also very slow, it'd be a little bit harder to say which individual we would favor. And so that's kind of the kind of natural mapping of our of how we're bringing all these things together. And so we put all those things together. We modeled that with a so-called fitness function, which you've seen before, but now the fitness function serves to bring all of those optimization objectives together, all of those characters, that phenotype together. So this here we're referring to as the phenotype. And this is the fitness. The F then is the fitness of that phenotype. And so if we have a way to take all of those optimization objectives, combine them together in like a scalarization and create a fitness function F, then we could use a standard genetic algorithm to solve for that particular outcome. But like I said, we actually, the difference between what we're doing now and the previous single objective optimization algorithms is we don't actually want to converge on one single strategy, on one phenotype. We want to give a population. So we would like the output of this thing to actually be a community. So that's the term that I'm going to use here, where if we've got our different characters, F1 and F2, then as we've described, we will have a Pareto optimal frontier, and there will be phenotypes in our target solution set that are spread along that frontier. And I will sometimes refer to this frontier as an ecological community. And each one of these spaces will be a niche. So in ecology, if two species fill the exact same niche, the one that is slightly more efficient will take over that niche and crowd out that other species. That's the notion of what's called competitive exclusion. And this is the reason why we have so-called niche separation in ecological communities. If you walk out into a forest, you're going to find a bunch of coexisting organisms of different species. They coexist because they inhabit different niches. From an optimization perspective, what that means is that there are different trade-offs that they are all that what. So one of them ended up saying, I'm going to take over the speed niche, and so I'm going to be really fast, and that's going to end up maybe affecting my basal metabolic rate, but that's the trade-off I'm willing to make because I'm going to get all the benefits of being fast. Another organism is going to be slow, like a sloth, but it's going to have a really low basal metabolic rate and maybe won't need as much energy, and it'll need to also have other characters that go along with being slow that that give it benefits despite not having the benefits of being slow. But then that's how the sloth can coexist with the hummingbird. So you have these two very different organisms that sit right next to each other. They're not competing because they live in different niches. And so you'd say, well, what is the best robot to build or whatever? You want to build a hummingbird robot or a sloth robot? That's going to depend upon other things, but all of those good ideas can exist together. So we refer to an ecological community basically as a set of good ideas. And those are separated from the inefficient set, which are a set of bad ideas. So organisms in nature that were in this space didn't survive because of Pareto movement. If there is a Pareto movement, then that means that some other organism could have varied in such a way that will beat you in terms of all of the optimization criteria, all of the characters simultaneously, which means they will have a fitness advantage. So selection naturally pushes you this direction here. But then once you're at this here, because selection is degenerate, fitness is, so in other words, because we're mapping all of these characters to a single fitness function, there's a lot of room for diversity. And that degeneracy, this is multidimensional, this is a single dimension, is what provides for diversity along here, which is how you get coexistence. And so that's the mapping that we're thinking about here, is that we want a community of solutions that all fill a different niche. And then our stakeholder will say, the niche I want to fill, I want to be the fast robot guys. So just give me the fast robot solutions. The other ones will say, no, I want to be the really long-lasting robot guys. Okay, well, give me the long-lasting solutions, and so on and so forth. So that's kind of the picture that we're doing here, and that's kind of the mapping. So does that mapping to this kind of community ecology perspective, does that make sense what I'm saying here? A community of solutions. Let me make sure there's comments online here. All right, I see. Do we have to weight any of these individual fitnesses? No, that's the beauty of this whole approach. There is, if you were to weight these, if you were to say a priori that F1 is 5 times more important than F2, then you would be effectively collapsing this space into a single optimization space where you've already chosen a niche. So you can think of this niche here as a choice where F2 is much more important than F1. You can think of this niche down here as a space where F1 is far more important than F2. And so we aren't going to choose the relative importance ahead of time. We're just going to say, we know it's better to be higher in what, as long as we know which direction is better, then we can come up with this community, which is all of those choices all at once. Okay. All right, so because of this, we can't use a standard GA because a standard GA would require us to scalarize. And so we need to do something a little bit more in our selection operators. So typically, in all of the different multi-objective genetic algorithms that we're going to talk about and eventually converge on one approach here at the end, probably the end of next lecture, that is that we need to come up with sort of a clever way to define fitness and a clever way to do selection so that we don't accidentally turn a multi-objective problem into a single objective problem. And so how do we do that? And so again, remember the goal is to find a set here. So find the Pareto front, all of it. That's our goal. We'll never find all of it. The ideal would be sampled uniformly. All right, so then, so there are a number of different approaches that have come up over the years. So class 1 approach, so you can find several different varieties of this, are the so-called weighted sum approaches. Or that's what I'm kind of classifying them. And so in this case, in the weighted sum approaches, it's a traditional GA for the most part. But we are going to incorporate a weight vector, W1, W2, and so on, all the way up to Wn, into the chromosome. So as part of chromosome. And then so each solution will have different weights. And then we calculate the fitness of each solution based on its weights. So this is a little weird in that each individual gets a different fitness as the other. So we'll calculate individual fitness with that individual's weights. All right, so that's like I randomly have my genotype. On top of that, I randomly believe that, or I randomly have a preference for speed over energy use. And so when my fitness is calculated, it's going to calculate my speed and my energy use and weight them with my weights. But another individual might even have my same genotype, but they'll have different weights. And so they will have a different fitness for the same genotype. And so we are incorporating all that in there. And the idea here is that it's a heuristic that optimizes multiple objectives simultaneously while using a much longer or larger chromosome. So that's a trade-off here. So that's one example. Yeah. That's so yeah. Is it a convex combination? Is it a conical combination? That's kind of like the question here. I don't. So traditionally, these weights. Traditionally, this is a convex combination, which just means that the weights add up to 1 when we do multi-objective optimization. Off the top of my head, I don't know if in these weighted sum approaches, they always make that requirement, or if they do, because like they might normalize right at the end. So you can imagine as you're doing your mutations and your crossovers or whatever, then you're not going to meet that constraint anymore because you might screw up some of these things. But then right at the very end, if you do all that mutation, all that, you can add up all your weights and normalize them all, then they'll all add up to 1 again. So off the top of my head, I don't remember how they handle this, but traditionally in multi-objective optimization, you use a convex combination of these weights. So I think that is the case, but I don't know off the top of my head. And there are multiple, in the literature, you can find approaches that follow this form. There's sort of different varieties of them. Okay, so any other questions about that one?
Hello?
This basic approach. Yeah, there's a question online?
Yeah.
Oh, it's 11:45. Go ahead.
Who sets the weights? Like, do we set it, or like is it set by the algorithm on its own?
So the question was, who sets the weights? These weights are drawn randomly as if they're part of the chromosome. So it's just, you're just augmenting the chromosome. But we'll pick up there next time. Meanwhile, I guess it's Tuesday, so yeah, see you Thursday. And thanks for going over a minute with me. Sorry about that.
You mentioned something during the lecture about the solution project. One said how they were, some of them were scattered over different peaks.
Yeah, depending on how you set up your algorithm.
Right, and mine did do that sometimes, but I thought you only wanted the plot of the thicknesses. You didn't actually want the solutions plotted, but with the original function and showing how they're.
Well, I'm not gonna take off, but the intent was, and I've sort of, I think, updated the document for the future, is that instead of plotting, you plot the optimization objective as well as at least your terminal solution that you found, if not the whole terminal population.
Yeah, I didn't know that.
Oh, that's fine. And we're not going to
resubmit, or?
I mean, if you want to, you can.
Okay,
That
I'll
would
check
be,
it out just for me. But
yeah, I mean, that ends up just being a much more visual way to evaluate the quality of the
to see
solution.
where all the solutions lighted up with respect to the overall actual function that we would
Right,
plot.
yeah. I mean, if you plot all of them, ends up being pretty interesting because sometimes you find that they are all on 3 different peaks, and then they
Right.
won't be in any of the valleys. But if you just plot the one, that at least shows that oh, I can definitely see visually that's the peak I wanted, and it did find it.
I want to do more interesting stuff, but you also mentioned not confusing the TA.
Sure,
rating,
sure.
So
Right, no, that's fine. Let me
Yes, sir.
let me end the meeting here. Were there any other questions online, real quick?
Yes, I actually have. Well, I was just listening into the conversation, and yes, that's one of the questions that I had. I plotted the terminal population, and I also spoke with the TA who told me I should do several iterations and then plot any error bars that I find, which shows which one has a better algorithm. Is that the approach you were looking for? And the second question is regarding the second mini project, if you don't mind.
Regarding error bars, you can do that. That's fine. That is going above and beyond. I think that's an excellent suggestion, but in the rubric is not something that we're going to be formally looking for. So that would be the professional way to do it, is to run GA multiple times and see what the error bars are. I was hoping for, at the minimum, you'd run it once and then plot your terminal population, so you get multiple dots on the same function. But it's totally okay to just plot the terminal point. But because I didn't say anything about that, if you just plotted the function, but then in the text said, look at the function, this is the optimum, my GA produced this, and so those two are a match, that's fine too. But I was just saying that the intent was to imagine visually on top of that plot, you could show that that's where the point was. Does that make sense?
Thank you very much for the clarification. I've done both, so I think I'm
Okay.
covering that front.
Sounds good.
Yeah, my second question is regarding the second mini project. It's kind of open-ended, and there are suggested problems. So my question is it possible to, for instance, just pick up a problem at random that's saying, I'm going to use negative selection to define, here is the self, which is a range of integers that is acceptable. Anything outside of this range is not acceptable, and then do detectors and all that. Is that a sufficient enough of a problem?
That sounds fine. If you wanted to work on mini project 2, which I think is one of the more challenging mini projects, but if you wanted to work on mini project 2, then that's fine. It's kind of up to you. If you would say, I want to demonstrate negative selection and I'm going to come up with a sample toy model where I can demonstrate how negative selection works, I think that's great. So, so then you can definitely feel free to do that. So there's a lot of flexibility. You don't have to use the examples that I gave. You just have to sort of demonstrate a principle from either the artificial immune systems or the genetic programming, or both.
All right, and if we do if I do the artificial immune system, then can I just do negative selection, or do I need to do both clonal selection and negative selection?
I think as long as you have a compelling demonstration of negative selection and how it's working better than, say, chance or something, that would be fine. I'm just asking you to demonstrate one concept. And so, you know, I wasn't specific saying you need to pick 3 concepts or whatever. So that I think would be enough, demonstrating negative selection.
All right, and what? Sorry to elaborate even further. The demonstration doesn't have to be very complex. Can we do just one variable, or do we need to do, for instance, a decision, multiple decision variables? Like it's a vector that has multiple elements, and we compare over all those elements.
No, it doesn't. It's kind of similar complexity as mini project 1. So if you can demonstrate negative selection using a single variable, maybe you look at its binary representation and maybe that gives you enough features to do the negative selection over or something, then that's fine. So as long as it is a compelling demonstration that you're actually using negative selection and not something else that's simpler than that, then it's fine if it's a single variable.
All right. Thank you very much for the clarification, sir.
Uh-huh.
All right. Have a good one.
Okay. And for anyone else online, I am about to end the meeting. I've got a couple of others in class. So if you have any other questions, then please feel free to send me a note, or I'm happy to set up office hours. Otherwise, see you Thursday.